now we're going to look at two variable statistics, dependent, independent variable, right? So perhaps you go ahead and you want to measure the height of a tree as a function of a particular nutrient that you give it on a daily basis, right? So perhaps, or rather as a function of the amount of a nutrient that you give it. So maybe you run like 10 trials, 10 parallel experiments. You have this particular tree, 10 of them, you planted all 10 of them in parallel, right, in different areas, and then when you planted them, you know, you gave no nutrient to the first tree, maybe 5 milligrams to the second, 10 milligrams to the third, and so on and so forth. And maybe you got some kind of pattern like this. So let's say tree height, let's say after, let's say at 1 week, something like that, 1 week, and then this is milligrams of nutrient, and lo and behold, you got something like that, let's say. So you look at that data and you say, hey, it kind of looks linear, right? Or perhaps you got something that looked like this. Maybe you got some pattern that looked like this. You say, hey, it seems exponential. Okay. Regardless, the point of this is that, the point of this whole story is that you want to be able to quantify the reliability of your hypothesis or observation that the relationship is exponential or it is linear. And furthermore, you want to be able to get an exact equation. So for example, I may look at a scenario like this. I may get data like that. Okay? Line of best fit may go like this, right? And on another experiment, I may get data like this, whereby the data points go right through the line of best fit. Now, if you are, let's say, a manager of a company and you ask somebody to do an analysis on a prospective product, and they came back with this analysis for product 1 and this analysis for product 2, and let's say you as the manager of the company had the purse strings to give, you know, the person in the research and development department the millions of dollars to continue to research the product and spend money on marketing, which of these two, left or right, are you going to authorize? Of course, because that one has amazing correlation. It really does seem to follow that linear pattern. This one doesn't have the same extent. So regression analysis is a quantifiable way of, it is a technique, it's an analytical technique that will actually quantify what you can see here visually. That is to say, this would be 100% correlation. That is to say, if you went ahead and said the equation of this line is y is equal to mx plus b, whatever the m and the b are, I can say with 100% confidence that this data follows this equation, right? Maybe here you get the exact same equation, you see the same line. This one is also y equals mx plus b, but you only have maybe 75% confidence associated with that correlation, right? And how many of you guys have seen that feature on, let's say, Excel on a spreadsheet, regression analysis? So that's useful information. So there are two aspects here. There's the getting of the equation of the straight line, like what is m? Is it, you know, is it 4 over 5? Is it 6 over 2, etc., etc.? And what is the y-intercept? Is it -3, and so on and so forth, okay? Now, in order to, for a linear analysis, in order to be able to figure out what m and b are, you need to know some differential calculus, which you guys don't know. And if you actually take a look down here in my little note, I think I actually do go through an example of it. I'll show you where I actually calculate the y and the, I'll go back up to the top in a sec. Regression analysis. So, regression analysis is a means of developing a line or curve of best fit to predict the outcome of a function which is dependent upon one or more variables, i.e. 2 or more variable statistics, by taking actual data and creating a linear and nonlinear equation which minimizes, now here's the thing, oh, you don't know what residuals are yet, I have to go back and explain what those are. The sum of the square of the residuals between the created equation and the actual data point. I believe this was fully developed by, okay, who cares? Recall, okay. So, you see this equation over here? xi minus mu x. What is that? What's that all about? This is your average, right, of all of your data, right? Yeah, that's deviation, exactly. So recall that the square of the deviation is taken because the sum of the deviations equals 0 in all cases as provable. We did that in class, didn't we? Yes, we proved that if you just add all the residuals for a one variable statistic, you get 0. We did prove that. Okay, let's just see what I did here. Okay, here. Let's start by imagining that through some experiment the following set of data is collected. -2, -5, -1, -3.5, and so on and so forth. Although we don't yet have the equation of line of best fit, let's simply add it to our graph, recognizing that it's simply serving to illustrate the math that we will use. So if you plot all those data points, right? Let's say you plotted those 4 data points. There they are, 1, 2, 3, 4. Xi, yi is the general representation for the set of actual data points, 4 of them in our case. Okay? And it would be really nice if we could actually read what I wrote there. Because it converted it from Word 2010, it's nasty. This equation, meaning this line here, this is the equation of the line we were, Okay. Let me see if I open this up a little bit, we'll be able to read it. Okay. One of the 4 residuals in our sample problem, it is equal to, how am I going to teach them this stuff? Okay. So, in this case, our residual is going to be as follows. -3.5, okay? -3.5 is 1, 2, -3.5. That corresponds to the y coordinate of this actual data point, agreed? And what do I mean by -3.5 minus this? What do you think? The alpha 1 minus 1 plus alpha 2. What does the minus 1 correspond to? What are the coordinates of this data point? -1, comma, -3.5. So, I just want to move my little cursor here. So, in other words, this line is going to be a predicted line of best fit for the data, right? And a residual is going to be defined as the difference between the height of an actual data point, okay, in this case it's -3.5, to the height that the equation of best fit predicts will occur at the x coordinate of this point. And the x coordinate of this point is -1. So when x is -1, the actual data is at a height of -3.5. But if you use mx plus b, right, the height of the data at -1 will be whatever your equation says times -1 plus b. So the idea here is that alpha 1 and alpha 2 represent slope and y-intercept. Okay, you don't know what they are. That's what you're trying to figure out. So what you do is you simply say, hey, if we set this thing up for this whole thing as the sum of the square, we call that a residual, by the way, that distance a residual. If we take that value and we square it and we add all of those up, let's set alpha 1 and alpha 2, the slope and the y-intercept. Let's play with the angle of this line, right? And the up-downness of the line. The angle would be the slope, the up-downness would be the y-intercept. Such that the sum of the squares of those residuals is a minimum. The moment you use those words, you're talking about calculus, right? Minimize, you're minimizing a function. Now the problem is, most of you guys haven't taken calculus, and those of you who are taking calculus in high school know how to differentiate one dependent variable as a function of, a dependent variable as a function of an independent variable, dy by dx. But the problem is, you're going to have 2 independent variables, alpha 1 and alpha 2, which means you have to take a partial differential with respect to each. That's something you'll learn, I don't think they teach you, you don't even learn that, you don't learn that in AP Cal. You'll learn that in university. If there are any of you who are interested and want me to take you through it, let me know and I can take you through it, after school one day and I can show you. But the bottom line is, this is what the math will look like. It's really cool because it uses sigma notation as well. So what you have here is, no, you are not expected to know this at all. Ri represented that distance between -3.5 and the actual function. I square it and I add it up for all of them. Remember the sum of the squares of all of the residuals? And it works out to that. And when you go through a whole bunch of math that you guys are not familiar with yet, oh shit, you gotta take that swearing off of the, yeah, Jun, mark the time. You have to edit that profanity. You are taking calc are used to seeing solid D's like that. You're not using to see partial D's. But the bottom line is, when you go through this math, you do end up getting this. Y is equal to 2.2, there's your slope and there's your y-intercept. And then I double checked my work because I went to Excel and look, what did Excel give me? 2.2 and negative 0.9, right? So Excel will do the work for you, but the math that it's doing is the math that I did above. Now, you didn't learn how to do partials. And you definitely didn't, right. So, is there anybody here who'd be interested in learning that? 1, 2, okay, we'd have to book a class one day. That's not something we can do in class, okay? And I'll show you how to do it. The other aspect of it is not only am I getting the actual equation of the line, but I'm also getting a confidence here of about, what is that? I can't read it. What is that, 94%? 98? What is that? I can't read it.
98.7.
Yeah, so about 99%. So, in other words, the data is fairly well clustered around the predictive line. As you can see, this guy's a little shifted off and so on and so forth. There's a different mathematics associated with that. Okay? The beauty of this course, from your perspective, since your objective is just to get marks, is that you don't have to know any of the hard stuff that goes behind it. You're literally going to use a graphing calculator and it'll do all the work for you. Those of you who are interested in knowing how it works, I'll have to teach you some math after. Okay? So, literally, when it comes to the graphing calculator, what you guys will do is you'll put in the data, right? You'll graph the data. You'll look at the pattern. If the data looks straight, then you're going to do a linear model for it. If the data looks exponential, you do an exponential. If it looks quadratic, you'll do quadratic. And we'll go through different cases. You'll tell the calculator, please give me an equation of best fit for this quadratic model. It'll give you a quadratic equation, and then it'll also give you a reliability, like a percentage. Okay? Do you guys sort of understand what I'm saying? All right. Now, let's go back, to the beginning of this thing, because maybe we can actually talk a bit about two variable statistics. Okay. Talk a bit. Okay, so correlation coefficient. Correlation coefficient is a quantitative measure of the spread of data about the equation of a line of best fit. So again, it's that percentage that I was talking about, the reliability, you guys with me? For a line. Arrived at by Carl Pearson, whereby lines with positive slopes have values ranging from 0 to 1, and lines with negative slopes have values ranging from 0 to negative 1. So if you were to take a look at this, let's say you had this scenario, maybe that's going to be 99%, but in a scenario like this, that would be minus 99%. Got it? For straight lines. Perfection is going to be what number? 100%, 1 or 100%. But with positive slope. Perfection with a negative slope for straight lines is going to be negative 100%. Now it's important that you remember that correlation coefficient that I'm discussing, again, applies to straight lines. Because we're going to be using a different thing for nonlinear stuff, and it's going to be called coefficient of determination. So for straight lines, for positive slope stuff, you run between 0 and 100%. For negative slope, you run between 0 and negative 100%. So negative 100% is actually perfect correlation for a straight line that slopes downward, right? Jeremy, you're cool with this so far? Okay. Let's see how much more we can get done. We'll probably go for another couple minutes. Okay. It is effectively the two-variable version of, okay, so correlation coefficient is effectively the two-variable version of variance. You guys remember what variance was? For one variable statistic? It's the sum of the squares of the deviation, the average of the sum of the squares of the deviation. It's sigma xi minus mu squared over capital N for a population over n minus 1 per sample. So this thing is going to be the two variable version of that, sort of, okay? Two variable version of variance, which is applicable to one variable statistics, whereby instead of giving quantitative assessment of spread above the mean for a one variable statistic, it provides spread above the line of best fit for a two variable situation, okay? So instead of giving us spread about an average, it's giving us spread about the line of best fit. Does that make sense? Does that make any sense so far, Ken?
Yep.
Okay, recall that variance for a population, the n minus 1 versus capital N variation for sample also applies for correlation coefficient. And recall that it was defined as the average of the squares of the deviations of all the data. So you see that equation there? Sigma x squared is equal to sum of, you guys see the variance is right there? That's the variance, agreed? Remember, we talked about this, right? Okay, and remember this too. We proved this, right? Remember, we don't use this because it always works out to be 0. That's why we use that, right? And we didn't use absolute value because of capital. Okay. Know that the units of variance are units squared unless standard deviation is used to provide a measure of the spread in the same units as the variance. I may not have mentioned that if one prefers to make things more general, that is to say to be able to compare the measurement of spread between different variables, a unitless measure of it can be, okay, using z-score. We did talk about z-score. So you already know about that, right? So you know about z-score. Oh shoot, now I'm going to teach you this. So there's z-score. I taught you about z-score, right? X minus a data point minus the average over the standard deviation tells you how many standard deviations you are away from the average. Now, whereby mu zx is now 0 for all cases. So what I'm doing right now is there's not going to be enough time for this. There's not going to be enough time for this. I'm rewriting variance not in terms of x, but I'm writing it in terms of z-scores. Who knows what I'm doing? Like I'm taking every x data point and I'm changing it from a data point x to the number of standard deviations it is away from the average. Like I'm taking every data point, I'm going minus mu over sigma. So I'm normalizing it. Now, of course,
is this going to be on the
what's it? No. I'm trying to. You guys understand why mu zx is 0?
It's not going to be on the test now.
Because how many standard deviations are you away from the average?
0.
Okay, so you understand a little bit. Okay. I just don't like to give you guys formulas for the sake of formulas. Okay, so for two variable statistics, instead of variance, covariance is utilized to measure the spread about a line of best fit. Generation of the equation of that line of best fit will be discussed later. Good, I don't have to show you the proof now, because I'm going to do it now. Here it is. So for two variable statistics, good. For two variable statistics, we don't use the term variance, we use the term covariance. And rather than describing spread about the average, we're talking about spread about the line of best fit. I use the same symbol sigma, but instead of writing sigma sub x, I write sigma sub xy, meaning it's a two variable statistic. Okay, and notice it's different. In the other one, sigma variance for sigma sub x squared, it was just like, this was gone and you had a square up here, right? Now instead of that, you have the deviation for x about the average of the x coordinates, right? Times the deviation for y, all average divided by the number of data points. Now the question is, do you guys understand why that works and makes sense? We don't have much time. So that's something that we're going to have to discuss tomorrow.
But this is going to be on the test.
No, not so much. I want to take you through why these things work, rather than just give you formulas. Then after we go through the theory, we can just do examples. I'll try and remember my laptop tomorrow.